Hello everyone, I hope you all are doing fine. In this lecture, I will discuss the memory circuits. First, I will show the classifications. Here, okay, before I start, let me tell, this slide is not prepared by me, I collected this. So for the classification, here we have first read and write memory that can be divided into two categories. First, random access and this non-random access memory. For random access memory, you can access at any location of the memory at any time by selecting the addresses and bit location. But for non-random access memories, you cannot directly access at any location at any time. You need to follow a procedure to extract or write data in certain location. In random access memory, we have two type of memory. First one is static RAM and second one is dynamic RAM. For static RAM, you just store a value in the chip, and if you keep the power supply on, then you need to do nothing. The value or the data will be stored there. But for the dynamic RAM, you will need to continuously refresh the memory to keep that memory valid or at the exact value. Otherwise, the memory or the data can be lost. And the non-random access memory, here we have FIFO, that is first input first output, LIFO, last input first output, shift registers, and content addressable memory. The next category is non-volatile read and write memory. Before that, I will discuss the ROM. ROM is a read-only memory. That means if you write some value, some data to a chip, then later you will be able to only read the data from that chip. You cannot erase or reprogram that chip. So this is ROM, read-only memory. We have two types of RAM, mass programmed and programmable ROM. And after that, we have non-volatile read-write memory. For the only read-write memory, that is volatile. That means if you turn off the power supply, the data will be lost. On the other hand, for the non-volatile read-write memory, once you store the data, then if you turn off the power supply, there is no problem. Later, when you will connect it to the power supply, then you can read the data. Here we have EEPROM, that is erasable and programmable ROM. This is like this normal ROM, but you can erase and reprogram this type of ROM. Later we have E2PROM, that is EEPROM, electrically erasable and programmable ROM. For the EEPROM, you cannot erase the ROM data electrically. You need to use a procedure involving UV lights to erase the chip. We'll see this procedure later. For EEPROM, you can erase the data from the chip electrically, and then again you can write or read from the memory chip. And finally, the flash memory, this is also one type of EEPROM. Here we have a memory architecture. This is the memory chip. We have m bit word, that means one word contain m bits, and we have total n words. If we want to select any word, then we have to use one of these control signals. But if we use one control signal for each word, there will be a lots of control signals that is difficult to handle. For this reason, we use decoder circuits. In this case, we can control or select a huge number of words using only a few control signals, that is here, and we can select any word from this chip by giving appropriate address to this decoder circuit, and this will select any one of the words. Here we have array structured memory architecture. this is the whole memory chip, and these are the bit lines and these are the word lines. We can select any word line using this row decoder circuit. Then if we want to select any specific column where we want to write data, or where from we want to extract data, we can use this column decoder circuit. Using these, we can select only a single cell or a few single cells from where we can read data or where we can write data. And these sense amplifiers or drivers helps us to read data from that particular cell or few cells there. Here we have another memory architecture that is called hierarchical memory architecture. Sometimes what happens, the memory chip is so large that if we use this architecture, then the row decoder circuits becomes one very complicated circuit. To reduce the complexity and enhance the performance, we divide this whole memory chip into blocks. Here this is one block. Now if we want to select this A address, that is a cell or a memory location that is located here, what we need to do first, we need to select this block. We do this by this block address selector. Then if we want to activate a certain word line here, that is done using this row address decoder. Then if you want to take a particular cell, then that can be done using this column decoder circuit. And the outputs from these the IO lines are connected with a global bus data bus from where we can extract the data, or using the data in that bus we can write data into the memory cell. This is the structure of a 6 transistor CMOS static RAM cell. So this can store 1 bit of data. Now we will see how does it operate and how we can read or write data from this cell. First we will see how we can read data from this cell. Let's assume if data, that is Q equals 1, is stored in this cell. If Q equals 1, that is this is 1, this location is 1, and Q bar is 0. Okay, as you can see, this is a memory cell and it is nothing but just two connected in this configuration. Here M1, M2, M3 and M4, these 4 transistors are used for these 2 inverter circuits, and M5 and M6, 2 transistors are used just to connect this memory cell with the bit lines. Now if the stored data Q is 1, this will be 1 and this will be 0, this location is 0. If this location has value 1, that is 5 volt, then this M2 transistor will be off, because this is 5 volt, this is 5 volt, and at the gate of this PMOS we have 5 volt, so this will be off, and this transistor will be on, because at the gate of this transistor we have 5 volt. And as this Q bar is 0, this will make this M3 transistor off and M4 transistor on. So we will have only M1 and M4 transistor in this circuit on if we have Q equals 1. Now when we want to read this data from this cell, what do? We picture these bit lines by a voltage that is Vp. This can be also considered a capacitor is connected with this bit line, this is Vp, and this will be also a Vp. Recharged capacitor you can consider this here is connected, that is Vp. Now this word line, this is selector line, is turned on. If this is turned on, this circuit will be on, this transistor will be on, and this transistor will also be on, because this location has 5 volt and this is the discharged voltage which is less than the VDD or 5 volt. So this transistor will turn on, and as here we have 1, then this as we have here VDD or 5 volt, and here we have VP, that is less than 5 volt, the charging current will flow in this direction. That will try to increase the voltage of this bit line PL. On the other hand, this here the voltage is 0, and this voltage at bit line is VP, that is greater than 0, and when the WL is 1, M5 will be also on, and a discharging current will flow in this direction. What we have here now, when we turn on M5 and M6, the voltage at BL will try to go will try to increase, and voltage at VP will try to decrease. From this differential change in BL and BL bar, there is a circuit component that is called a sense amplifier that will decide the value 1 is stored in this cell, and that will go to the data bus. So this is how we can read a value from this 6 transistor static RAM cell. Now let's see how we can write a data in this cell. For this, let's assume we have a value, that is Q1, already stored in this cell. In this case, M1 and M4 is on, and M2 and M3 is off. Now if we want to write a data 1, that is 1 is stored already, and we want to write 1 again. So what will happen? So first we need to make this line BL to 1, and this BL bar is 0. We make these values or the voltage level in this bit lines forcefully. Then WL is turned on, and we can see this point has voltage 5 volt, this point has also 5 volt, and this is also 5 volt. So this transistor will not turn on. So, and for this transistor, here we have 0 here, and we have 5 volt here. So this transistor will also not turn on. So the value that was stored, that will remain the same. So we had a value 1 that was previously stored, and now the same value remains in this cell, because we try to write the same value again. Now what happens if I want to write a value 0, that is Q equals 0? For this, we first make this BL equals 0, BL line 0 and BL bar 1. We forcefully make this maintain this voltage level at BL and BL bar. Here we have 5 volt because we turned on the WL, and here we have 0. So this transistor will turn on, and this Q point will certainly be 0, because this is 0. When Q is 0, this location will also be 0, and the gate of this M1 MOSFET will also be 0. So this will turn off this transistor, and as this point has voltage 0, this will turn on this transistor M2. When M2 is turned on and M1 is turned off, this location, that is Q bar, will be 1, because this is a pull-up circuit here, and this is connected to VDD. Q bar voltage will be 1, and as this is also 1, so we have successfully made this Q bar 1. And when Q bar is 1, this will disable this transistor M4, and will turn on this transistor M3. So when this transistor M3 is turned on, this location will again be 0. So now this cell is at a stable condition, where we have 0 at Q and 1 at Q bar. In this way, we can write 0 in a cell where the value 1 was stored previously. In the same way, we can write 1 in a cell where the previously stored value was 0. In this way, we can write in a 6 transistor CMOS static RAM cell. Now we have 1 transistor dynamic RAM cell. In this case, we have this capacitor CS. This is the main storage component. If we want to store a value 1, this capacitor will be charged to VDD or value 1. And if we want to store a value 0, this capacitor will not be charged, or it will be discharged to 0 voltage. Now let's see how this happens. First we want to read the data that is stored in this cell. Here this is the bit line and this is the WL, this is the word line. To read the value, this bit line is charged to a value VDD by 2. You can consider this as a capacitor is connected with the bit line. Now the WL is turned on, so this BL is bit line has a voltage VDD by 2, and this is turned on, that has a voltage 5 volt. So this bit line will be connected to this capacitor. If the value that is stored in this cell is 1, the voltage across this capacitor will be VDD, and this will try to increase the voltage of this capacitor or bit line. And if the value at if the voltage of here at CS is 0, then this will try to decrease the voltage at this bit line BL. From this change in the voltage of bit line, the sense amplifier will determine whether the stored value is 1 or 0. In this way, we can read the value from this cell. But one important thing, if the stored value is 1 or 0, whatever, when we perform this read operation, the charge or the voltage across this capacitor changes. So this can alter the stored value. So we have to take a special precaution so that this type of contamination does not occur. For this reason, whenever we read a value from a dynamic RAM, the value is again written to this cell, or the value is refreshed here. Even if we don't read from this cell, here as we have MOSFET and this is the capacitor, there can be leakage current. Say I have stored a 5 volt here, but that is value 1, but by the time the voltage can decrease. To prevent this, we need to refresh the data after a certain interval, and we need to continue this refresh to safely store this data here. Now we will see how we can write a data in this cell. For this, first we make if we want to write 1 in this bit line, we make this the voltage of bit line is VDD, or we can consider that this capacitor is charged to VDD. Now the WL is turned on and this capacitor is connected with this bit line. So if the value I want to store that is VDD, then this capacitor will be charged to the voltage VDD minus VT, that is the voltage drop across this transistor. And if I want to store the value 0, then I will keep this the value of this bit line to 0, and this capacitor will be at 0 voltage, and then the WL line is turned off and the value is stored in this capacitor. So in this way we can write 1 or 0 in this cell. Then we have this 3 transistor dynamic RAM cell. Here we have 2 line for read and write separately, and 2 bit line connected with this. And this is the storage capacitor. We store that data here, and the other transistors are used to read and write data from this cell. First, let's see how we can read data from this cell. To read this data, we recharge this bit line to a value VDD. You can consider a recharged V capacitor with voltage VDD is connected to this bit line. Then this RWS line is turned on. Here we have 5 volt, and at the gate we also have 5 volt here. Now let's consider we have stored the value 1 in this cell. That means the voltage at X will be almost 5 volt. This will turn on the transistor M2. As M2 is turned on, the voltage at this point will also be close to 0, and this will also turn on the transistor M3. So M2 and M3 both are turned on, and this bit line BL2 will start to decrease through these transistors, and the sense amplifier will sense this change in voltage level at bit line and determine the stored value is 1. Now if we had 0 at X, then M2 will not be on and M3 also will not be on. In this case, the voltage at this bit line remains VDD, and again the sense amplifier will determine, in this case, the stored value is 0. Now we can see when we read the data from this cell, only the right part is active and the left part is inactive. So you can say M2 and M3 transistor is used only to read data from this cell. If we want to write a value in this cell, what we do? First, we make this bit line equals to the input data that I want to write in this cell. That means if I want to write a value 1, we make this value VDD, and if I want to make this store value 0, we make this bit line voltage 0. Then this WWL line is turned on, and this will connect this X node with this bit line. If the voltage at VL1 is VDD, this capacitor will also be charged at VDD minus VD. And if the voltage here is 0, then the capacitor will get also the 0 charge, and the voltage across it will be 0. In this way, we can write 1 or 0 in this cell. So far, we have seen the circuit configuration of RAM. Now we will see the ROM, read-only memory. So here we have MOS NOR RAM structure. So what happens here? This is the word lines. We can select any line using the decoder circuit, and this is the bit lines. Here these PMOSs are used as pull-up networks or pull-up devices. So if I select, before I say how does it work, I hope you have a clear understanding of ROM. That means we can only read value or data from this structure or this chip. So the value is already stored in the chip. Now we can only read from this. If I want to read the data that is written in the word line 0, what I do, I select this word line and take the data from this bit line. Now let's see what I'll get. Here this is a ground line, and this is also another ground line. When WL0 is 1, these points, junctions are not connected. A connection is indicated by a dot here. You can see this is connected here. So we have a MOSFET here, and the gate voltage is 5 volt because WL0 is on, and this is also connected with ground, so this will turn on. If this turns on, then the voltage at this point will be 0. Otherwise, the voltage at this point will be 1, because when WL0 is on, WL1 is off. So this transistor will not turn on, and this line will not be connected with the ground. So as this line is connected with a pull-up device, so the value of BL0 will be 1, but the value of BL1 will be 0. And again, BL2, at BL2 there is nothing in this line connected with ground, and it is connected with a pull-up device, so the value will be 1, and again here we will have 1. So we can say, where we have a transistor, if we have a transistor at a junction, then that value will be 0. That location will hold a value 0, otherwise that location will hold a value 1. For the word line 2, if we consider this, what will be the stored value? The stored value is here, the stored value is 1, here we have 0, here again we have 1, and again we have 0 here. Okay, so I hope now you understand how this ROM, this NOR ROM works. Now if I want to prepare a ROM, or want to write a or program a ROM, how can we do this? I'll discuss it now. At the beginning, when the chip is fabricated, a transistor is fabricated at every junction of this chip. For this example here, we will have 16 transistors at 16 junctions, but when we need to program this, that means I want to write some data. For word line 0, I want to write a value that is 1011. So I'll find the location where I have to write a 0. Then I will just connect this drain of the MOSFET with this bit line. So how we can do this? Here is the layout of previous ROM structure. So you can see this is the word line 0, this is the word line 1, word line 2, word line 3, and here is the ground. So we have the MOS structure in this cell, and we want to connect this metal line, and this is the metal this BL1, BL2, BL0, this is the metal lines here. If I want to connect this MOSFET drain with this BL0, then I just put a metal connect here, which connects the drain of this FET with this metal line. So this is how we can program this NOR RAM. Similarly, you can see for these other MOSFETs, here we have also this metal connections that connects the gate of the MOSFET with the bit line. Here we have the setup, that is MOS NAND ROM. In this case, we take the output from these locations just after the pull-up devices, and the other part is connected to the ground. The other part of bit line is connected to the ground. So what happens here when we want, okay, the word lines, these line voltages are kept at 5 volt or logic 1 at all time. When we want to read data from one of this line, we make the voltage 0. For example, when I make the voltage 0 here, what will happen? For this bit line, this ground is connected here, and this is connected with the output BL0. The voltage at these points are 5 volts or logic 1. If the voltage here is 5 volt, then this transistor will turn on, and this will connect this ground with this output. So the value stored here at this location of word line 0, I can say 0. When this is 0 and this is on, this transistor is on, so this voltage is 0, this is 0, so this transistor will not turn on. So this disconnects the ground from this BL1, so the value stored here is 1. So the value of BL1 is 1, so the stored value is also 1. Similarly, here we have 0 and again we have 0. So we get this value. So in this case, where we have a transistor, we have a 1 there. So at each junction we will check. If we have a MOSFET there, then the value at that location is 1, otherwise the value is 0. So what value is stored in this line WL2? That will be 0, 1, this is 0, this is 1, this is again 0, and this is 1. So this is the structure of ROM. Now we will see the structure of EEPROM, that is erasable and programmable ROM. The structure remains the same, but the MOSFETs that we have used, this is the general metal oxide semiconductor FET, but for the EEPROM we will use a special type of transistor that is called FAMOS, that stands for floating gate avalanche injection MOS. So what happens here, in normal MOSFET there are one gate and oxide, but in this case a metal layer is implanted inside the oxide, and this is called the floating gate. So what happens, if we put a high voltage at the gate and drain, the current will flow, but as the thickness of this T-ox here is very low, some electron just jumps to this metal floating gate and remains there. So what is the effect? The effect of this is the threshold voltage becomes higher. So initially if I put 5 volt here, a channel will be created here, and with this 5 volt at drain, this will start the conduction. But when some electron remains here, even if I put 5 volt, this will not create any channel here. So this increases the threshold voltage of this transistor. So in this way we can disable some transistors from our chip, and this is how we can program it. And now what about erasing? How can we erase this? We cannot erase this electrically because there is no way we can remove these electrons from this metal layer to this semiconductor electrically, but there are some other ways. If we excite these electrons with ultraviolet lights, then it will jump from this level to this metal layer or in this layer. Then it will be like a normal MOSFET, and we can again program using these high voltages here. After this we have the EEPROM, that means electrically erasable PROM. For this ROM we use another type of transistor that is called FLOTOX, floating gate tunneling oxide transistor. In this case what happens, this is the gate, and here we have this floating gate here. The difference between the previous one and this one is we have a floating part of gate or above the drain, because you can see drain, this is the drain portion, and we have gate hanging over the drain. So this is the floating gate over the drain. So the same thing happens here, but the difference is electrons does not jump from this substrate to this gate, but from this drain to this gate. So we can connect this drain to a high voltage and gate to a particular voltage to put electrons at this floating gate. And again, when we want to erase, we just reverse the combination of voltages and erase electrons from this floating gate. This is how we can electrically erase the data from this chip. And this is how EEPROM can be written, and the read operation for all ROM is almost similar. We can use the same technique to read data. And that's all. Thank you.